So, bonjour tout le monde. Hello everyone. My name is Kevin and this is Christophe. We both come from Criteo, which is a French company that does advertisement retargeting. And we are here to talk to you about debugging. So to give a bit of context, why debugging? Criteo process like 200 billion HTTP requests per day over thousands of servers. And when you work at that scale, every tiny random bug, the kind that has less than 1% chance of happening, is absolutely guaranteed to happen on one of your production servers. And so we are part of the Criteo Performance team, and as such, one of our jobs is to help developers diagnose this kind of issue when they happen in production. And we noticed through our investigation that we tend to approach the issues with a particular mindset, and that's what we'd like to share with you today. So this talk will really focus not on the tools, but rather on the methodology behind those investigations. So I was talking about a mindset. What is it about? It's very simple, in fact. The first thing to do when you are faced with a complex issue is to gather as much data as you can. It's very tempting to jump directly on your tool, and I still do it from time to time, but you really shouldn't. You really should try to understand as much as the context as you can, and more importantly, you need to make sure that this is data that you can trust. You have no idea how many hours we lost investigating stuff based on false data. So once you've gathered all the data that you can, the next step is to try to understand what it means. And it's usually the step where you will start using a debugging tool or profilers to understand better what it means. The goal of this step is to make a hypothesis, a theory about what is going on with your application. And once you've done that, the last and very important step is to actually verify that what you think is true. And more often than not, you will find that your theory is wrong. And it's okay, because in the process, you will have learned more stuff about the issue. And so you can use this new information to go back to step one and try again until eventually you manage to solve the problem. So to illustrate this, we took two investigations that are a real problem that we faced at Criteo, and well, we are going to tell you about them. Yeah. So most of our production incidents start from the monitoring dashboard. So Christophe, could you walk us through it?
Yes, so we are working in the WebScale team, which is like a team under all the other application teams, and they have their own graphs and boards related to metrics related to the business. And when they come to us, it's usually when there is a problem at the CLR, at the runtime itself. So we have this kind of, so maybe I will have to talk like this. We have this kind of board where you can see a lot of stuff related to a .NET. Okay, and what I want to show you is the kind of thinking we have to keep in our investigation. So we'll take an example, and let's say if we have okay, so it's not working, but anyway, this is the demo god. The demo god are not with us today, but if you go at the CPU usage level, and let's say we have an increase of the CPU usage, what could be the reason for CPU usage? That's the kind of reasoning you have to take. So it can be like we have plenty of exceptions over there, so we need to find a correlation between this and this one. And you could also have a bunch of requests coming from the outside world to our servers, and so we can see an increase of requests that could impact the way the garbage collection is working in our application. Or you can imagine even weirder explanation that could be you have more threads doing some contention, and if you are using spin locks in the code, then you will have like an increase of CPU because the code is spinning, doing some while loop before going into kernel mode. So that could be some of the reason. When I left university in 1989, after a degree in artificial intelligence and expert system, we used to call that kind of thinking called abductive thinking. Okay, so we've been told to add a cat into our presentation, so it was in the first slide, to use buzzwords. I've used the buzzword, so now we can start the real technical stuff.
Thank you, Christophe.
You're welcome. Okay, so
Wow.
yeah, real stuff.
So you managed to mess up with PowerPoint.
Yes. Okay, so let's start with the first example. And the first example starts with this part of the board that we have. So again, remember the first step is to gather as much information as you can, and you have to trust in what you are looking at. So you first need to understand what the contention rate is. So the contention rate is the number of time a thread tries to acquire a resource, but another thread is already having this resource. So the second thread has to wait, which is not good for scalability. So once you know that, and if you take a look at this nice evolution over time, starting at 15th of June, then you can see that the number of contention, and it's a rate, okay, it's not the number, it's the rate is drastically increasing over time. So Kevin, what can we say about that?
So as I said before jumping on your tool, try to get as much information as you can from this. So the first interesting thing about it is that it started on 15 June. So start by wondering what happened that day. In our case, it was easy. It was a new release. So it's pretty obvious that we introduced some kind of regression. Also, we see that the contention rate increased over time. So it seems to indicate that we have some kind of leak. And last but not least, it's not shown here, sorry, but the response time is stable, which means that whatever contention we have is probably happening somewhere in the background.
Yeah.
Okay.
Otherwise, the execution of the normal workflow would be impacted.
So that's about all we can deduce from this. So now we have to try to dig deeper, and we know that it's linked to the release. So the first obvious step would be to check the source code.
Yeah. So when you take a look at the source code and there is a new release, the easy stuff to do is to take a look at the changes that you have added to the new version. So we don't add like tens of changes, but like more than hundreds of changes for a release. And in our case, it's a kind of the easy case. Why? Because it's really related to a very specific C# kind of programming. You know, we are talking about threading, contentions. So you think about using locks. Maybe we have added some locks or some other pattern that could synchronize the access of a resource in the C# code. But we took a look at all the changes, and nothing was really related to this kind of pattern. So what would be the next step?
So when you are at this point, you finish with the boring part, and you can start having fun with your tools.
Yes, but you should not forget the boring part, okay? And we are serious here. You think that you like to be in the debugger, so Kevin love it, but sometimes the obvious step shouldn't be forgotten, okay?
Okay, can I have my phone now?
Yes, sorry.
Thank you.
Sorry about that. Sorry.
We want to know more information about the contention events. It turns out that in .NET, whenever two threads are containing a lock, there is an event that is pushed to ETW. So if we have a way to listen to those events, we will learn more information about what's happening. So there are plenty of ETW listeners available, but for this precise use case, I like to use JetBrains.trace, because it displays everything in a nice timeline view that is very easy to use. And so we took a trace on one of the production servers, and when we activate the log contention filter, then you get all those marks that remind me of DNA sequencing, and they each indicate one contention event. And when you hover the mouse over them. It's not working on the screen, but supposedly you would have a little, like this, a little window that tells you what is the method that triggers the contention. So the problem here is that we can do nothing with that, simply because we don't know what is supposed to be here and where is the regression. So luckily, we already know that we have some kind of leak. And we also know that it's not impacting the response time, so we can let the server run like that for a while longer. So what we did is we let the server run overnight, and the day after, we took another trace that you have here. And just at a glance, you can see that there is a lot more events. And by comparing the two traces, we can find that the contention, the new contention, is caused by the fire method in the timer QTimer class. So now we know where it comes from.
Can I go up? Can I just?
No, not yet.
Okay.
So we know where it comes from, but it begs new question. So timer QTimer seems related to timers, but how can a timer even cause contention? Yeah. So Christophe, can you go up to explain that to us?
The first time I have to go to do that in a conference. But, okay, so this is a kind of step where you usually happen. What I mean by that is that when you are investigating an application, maybe it's your application, so you know the source code and you have the source code. But maybe you are using third parties, or maybe you are using the .NET framework. And in that case here, the timer QTimer, it's just an implementation detail of how the .NET framework is managing the timer that your code is creating. So you need to take a look at how it's implementing. So you can use the website provided by Microsoft, the reference sources, or the source of .NET, which are very good. But I usually prefer to use a decompiler. So this is the decompiler I'm using. Use the one that you want. And I want to take a look at how the construction of a timer has an impact. So here, the construction of a timer, you pass the callback you want the timer to call when it ticks. If you want to pass a state, you pass the state, and you tell him when it should tick, and if there is any kind of repetition, you pass the period. Easy. So this code ends up calling timer setup with the same parameter, and in the timer setup, you see that the timer creates a timer holder, and the timer holder will get an instance of the timer QTimer class, the one that we've seen in the .trace DNA sampling that you love so much. So let's take a look at what the timer QTimer is doing. Remember, we passed the callback, the state, the due time, and the period if there is any repetition. So we create a timer QTimer, and it's really, really simple. The timer QTimer is like a POCO that keeps all the value that you have given to the creation of your timer. And that's pretty much it. So if we take a look at the timer holder class, it's even simpler. It just keeps track of the timer QTimer. So you would say, why would it do that? Because its only purpose is to ensure that if, unfortunately, you are working with not perfect developers, they might forget to dispose the timer. And in that case, this class implements a finalizer, and the finalizer will kick in after a garbage collection when the timer holder is no more reference, and it will close the timer. Okay, so we've seen the timer QTimer, the timer holder, and oh yes, we need to take a look at the fire method maybe.
Yeah, that's the one thing that I asked.
Yeah, I was just waiting for you to remind me. So remember, we are looking for the source of a contention. Contention is there is one thread trying to acquire the same lock as another thread, which already has the lock. So here you can see we have two locks. So we have one lock before calling the callback, and one other lock after having called the callback. So
okay, so now we know that fire can cause contention, but it's a lot of information all at once. So can you make a summary real quick?
Sorry, it's only code, C# code. So yeah. So let's draw a picture. When I'm creating a timer, under the hood, I get another instance of an object of the timer holder class that is referenced by an m_timer field from the timer object. That timer holder referenced the timer QTimer through an m_timer field, and the timer QTimer are stored in a linked list by the base class library of the .NET framework, and it's kept by the timer Q object in the BCL. So that's where we have a list of timers that are maintained in memory.
Great. So now we understand how timers work, and we're still wondering why we are using so many timers. Well, we have some contention, so there are two possibilities. Either we are using a lot of timers, or we are using just a few timers that are ticking a lot. And so to find out what is happening, it is time to use my favorite debugging tool, that is WinDBG. And so for that, we capture a memory dump on the production server. And then if we open it with WinDBG, we can run the dump heap stat command, which gives you a summary of all the objects in memory.
Wait. How many of you are using WinDBG?
That's a lot.
12. Okay. 12. Okay, good. Okay, so WinDBG lets you open a memory dump, and we can take a look at what's inside the address space and all the objects that I've mentioned in the code. So that we will be doing with scripting command.
So once you have executed the command, you can search the timer QTimer inside.
Yeah, because it supports Control F. That's one of the best features of the tool. I mean, the one who are laughing are the one who are using WinDBG. Timer, QTimer, you said?
Yeah.
Sorry.
Please focus.
Yes. Yes.
And we see that we have 14,000 instances of timer QTimer. So just like before, you cannot jump to conclusion after seeing that number. You need to know what is a normal number for your application. And from my experience in Criteo, our applications tend to use about 2,000 timers, which is already a lot. But here, clearly, we have like 12,000 timers too many.
Yeah, so I like the word clearly, because when I joined Criteo in the first investigation, and I end up in this kind of dumps, and I look at the number, and I see, what, you have more than 2,000 timers? We have a bug there. I will tell you. And Kevin said, no. We need a few hundreds for our Kafka subsystem, and a few other hundreds for this other subsystem. And so it might be funny when I'm telling the story, but it's very important that when you are doing an investigation, you know both the source code, as I have explained earlier, but also the numbers, the way your application is supposed to behave compared to the load, for example. Because in that case, this kind of number would mean a lot for you. It means like it's red and it's blinking. If you don't know these numbers, you will just pass through.
Okay. So then you can dump the individual instances of timer to see what they are doing. For that, you can use a dump heap -empty command. We executed it beforehand because it is a 20 gigabyte memory dump, so it takes a bit of time. And so if we click on the first one to inspect it, we see all the fields that Christophe told us about. Yeah. But we are interested in the timer callback to know what is this timer doing. So if you click on it, thank you, we have an instance of delegate. So with method pointer, supposedly you can find the actual method that is called, but I know no easy way with WinDBG to convert this value into a meaningful name. But fortunately, we have something into the target field, which means that this is an instance method. And just knowing the type that contains the method could give us enough information. So if we look, we now know that whenever this timer ticks, it calls a callback on meter metric. And we cannot deduce anything yet. So if we take another timer, so for instance, take the last one, so you don't have to scroll all the way. Just like before, we look at the timer callback, then at the target, and we see that this one timer is used by kafka.batching.accumulator. So now that we know how to retrieve the information from the timer, we just have to do that for each and every of the 14,000 timers in the list. So Christophe, please.
Like this guy. So yeah, sure, I will do that. Here you are facing the kind of issue that we are often facing at Criteo with this huge memory dump of the application with a lot of objects inside, and it's another kind of scalability. Okay, we're talking about runtime scalability for your application, but when you are debugging, also you don't want to waste your time clicking on stuff and just taking notes or using like an Excel spreadsheet. I'm pretty sure.
I like to waste your time.
Yeah, I know. You like that. So here we need to kind of automate some part of the search. So for that, you could use WinDBG. With this new version, you have a scripting engine based on JavaScript, but I won't use it. Sorry about that. Expectation lower. But I prefer to use C#. So Microsoft is providing a Nugget package called CLRMD, and with CLRMD, you are able to do the exact same thing that I've done in WinDBG, meaning that you can follow up the links going into all the instances. And I will show you that it's really, really simple. So I've written a tiny application. So is it big enough, the font, or a little bit bigger? No answer. So it's big enough. Okay. So in this library, you start with a data target. The data target type represents either a memory dump or a running application. Okay, you can do both. You can connect to a running live application or a memory dump. In my case, it's a memory dump. Then, from the data target, you ask for the you ask for the running CLR inside this process. Once you get the runtime, you can ask for the heap managed by the garbage collector in that application. And then, from the heap, you iterate on each and every instance of object that is stored by the garbage collector. So once you get an address, because everything ends up on an address, I know that the .NET language for this is a reference, okay? But in the API, it's an address. A reference is an address that can change its value. But it's an address at the end. Sorry, I have to make it quicker. Sorry about that. So once you get the address, you can ask for its type. So which type of object is behind the address that you've taken from the heap managed by the garbage collector? And here we are only interested in the timer callback, because this is what Kevin did by hand, asked me to do by hand. And once I get, I'm sure that it's the kind of object that I'm interested in, then I'm asking for the definition of its target field. If you have done some reflection in .NET, this is very, very close to what you are doing in reflection. You ask for the definition of a type, the definition of a field, and then, using that definition, you ask for the value stored in the underscore target field of the object pointed to by the address. And again, I'm interested in the type, because this is what I'm looking for. I want to count all the type in the instance of type that are referenced by the target. I'm adding them into a list, and I'm doing some very nice link code that I really love by grouping and sorting. So when I'm running this, I should get at the top the instance of, so I get 12,000 instances of meteometric.
So in short, we enumerated all the timer callbacks just to see what they tick for.
Yes. So I run it before, because it's 16 gigs and it takes some time.
So we see that we have 12,000 instances of metrics.core.metermetric, and this is the number of timers, of outstanding timers that we have. So it's a good coincidence. So at that point, it's safe to conclude that this is causing our problem. So the next step is to try and understand what is a metermetric.
Yeah.
So real fast. Nobody actually use metermetric. It is an internal type. Instead, the developer are using a wrapper that is named meter. It keeps a reference to the metermetric to a delegate meter property. The metermetric has an underscore timer field which contains a timer. And whenever the timer ticks, it calls a method on the metermetric. So now we have to understand what is keeping all of our metermetric objects alive. And I can really think of two possibilities. Either we have a lot of meter instances and we are still referencing them somewhere, or we forget to dispose the timers and they keep our metermetric objects alive.
Okay, so if you remember what I've said about the implementation inside the base class library, the timer holder class would be responsible for releasing the timer if we have forgotten. So I would start by looking at the meter hypothesis.
So the good thing about working with an expert is that he can save you some time by providing his valuable insight. So now that we know that it's almost certain that we are leaking meter objects, we can go back to WinDBG to check that. And the first thing we could do is to try and find what is referencing our metermetric object. So we could use a jcroot command for that, but it only displays one path to a root and not all the paths. And so we won't necessarily see all the referencing pointing to metermetric. So instead, I like to use another WinDBG extension, which name is SOSX. And it defines a ref command which displays the references going to an object.
And it's also faster. It's also faster.
And so if we call it on our metermetric, we see that it is only referenced by a timer callback and not by the meter object. So it seems to indicate that Christophe might be wrong on this point, but I have a hard time believing it. So we're just going to double check. And if Christophe is right, then we should have pretty much as many meter instances as meter metric. That's something we can check easily.
So we go back to the top and the pip minus stat, and we are looking for what is the
meter?
Meter. But we have plenty of meter.
Yeah, metrics.meter.
Metrics.meter. Okay. Yeah, I'm slow.
And here, if you can scroll just a little bit.
No.
Okay, we can see that we have 800 instances.
That's not enough.
Even though we have 12,000 meter metrics. So it seems really to point toward a mistake of yours, but let's triple check because I cannot doubt Christophe.
Thank you very much.
And,
especially in front of the audience.
Yeah.
Thank you very much.
So another way to verify what you said would be to iterate on all the timers, and well, the ones that are using by that are using metametrics, sorry, and check if they have been closed.
Okay.
So I'm going to no. I'm
but I
going
can use CLRMD to do that.
Yeah, but I want to be faster this time. So I like CRMD a lot, but the problem with that is that whenever you want to check something, you have to leave WinDBG, start Visual Studio, create a new project, import the NuGet package, write all the boilerplate code, script your thing, execute it, then go back to WinDBG. And I feel like this is a break in the workflow and also a huge waste of time.
Wow.
So I wrote this extension for WinDBG, which allow you to write C# code directly from WinDBG.
So what Kevin did, it integrated into the UI itself, but in addition, it's also I've written all the boilerplate code that I've been using, getting the memory dump, for example. Here it's WinDBG that got that. And so when you start to write with his extension, you see that directly you have this heap object. So you directly have the heap and you can start to write some code. So here, you want me to explain what you're doing?
Yeah, sure.
Okay, so he's using an extension method called getProxies, and the getProxies will return the list of all the objects for this type. So it's much easier than my loop, my big loop, when I enumerate. Here I just ask for a certain type. If it's a timer callback, then I want to ensure that the underscore target field points to a meter metric. Remember, we are only interested in the meter metric case. And so if this is the case, oh yeah, so I love this kind of code. So if you can try to follow what is written. So the callback has underscore target, and the underscore target will point to the timer. That points to, what is the name of the type of this one? Timer, maybe?
Timer holder?
Timer holder, and the time, maybe this is a timer, timer Q timer, and console.
Yeah.
I don't remember, too many timers.
So you can see that in under 1 minute we just wrote what Christophe did in his long Visual Studio program. Yeah. So it can save you a lot of time in when doing investigation.
I can give you more reason to use this kind of code, which is that this is C#. This is not reflection-like kind of code, so it's much more easy to write. And the extension that Kevin did, which is integrated inside WinDBG, is also available in your own tool, like what I've written. It's a DINA-MD extension.
Okay,
Thank
so
you, Kevin.
I'm not going to execute it live because it takes minutes and we are way late. But spoiler, it shows that Christophe is wrong in that one. So none of the timer has been closed.
Okay.
So clearly you don't know how finalizers works, Christophe.
Okay, so I don't know how finalizers work. So remember, we have 3 different steps in the kind of investigation, and the last one is the verify. So we have some assumptions, we make some hypotheses, and you need to confront the hypothesis with the fact. When there is something not matching, like here, because I definitely know how it's working, I'm expecting that it shouldn't be like this. So I've written a repro of the kind of code that you are describing. So here, I have an instance of meter metric that references the timer. And when I'm creating a meter metric, I create a timer, and I'm expecting that on the console I would see a tick, tick, tick every 1 second. And for the testing framework, In the main, I'm creating a meter over there, which is the one returned by this function. And then I'm calling the garbage collector, saying that please could you make some room for me? So since I'm not referencing this instance anywhere in the code, I'm expecting that the garbage collector will get rid of the instance, and after the garbage collection happens, the finalizer thread will kick in and see that this object as a finalizer will call the finalizer and will close the timer. So I'm expecting to see tick, 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 tick. And when I press enter, no more tick. Do you agree?
Go on.
I don't like your smile. Really. Control F5. And tick, 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 tick.
Okay, so maybe you're right
like
this time.
Yeah,
this time. But then, can you explain to me what's going on with the application?
Okay, so if we go back to the picture.
Because in the DOM, clearly the timers are not referenced, and they are not disposed.
Yes. So let's add the big picture with all the elements that we've seen in the investigation right now. So this is the Criteo view of the problem. So we have a meter that references a meter metric, that references a timer, and the timer will call a callback of meter metric. But here in the picture, we also need to add the base class library view of the implementation. So the timer referencing a timer holder, and the timer holder is referencing a timer queue timer. Agree on that?
Yeah.
What we've seen first in WinDBG is that the number of meter over there is not enough to explain between 800 and 12,000. It can't reference all the timer queue timers. And we have also seen with my tiny demo that my understanding of how the finalizer is working for a timer seems to be right.
So what's going on?
So what's going on?
Why isn't the finalizer being executed?
Okay, maybe it's because you didn't listen to me when I explain how the timer implementation. I'm pretty sure some of you have remembered the fact that the BCL is keeping track of all the timer queue timer through the timer queue object, and the name of the field is s_q, and S stands for static.
Okay, it's nice. You just explain why the timer queue timer are still alive, but it still doesn't explain why the finalizer doesn't kick in.
Okay, so when the garbage collector is trying to figure out if an object should be kept in memory, what it does a first pass of what is called marking. Marking, it started from all the roots, could be on the thread stack, could be a static, could be in the registers, and it goes down following all the fields of all these objects and mark them one after the other. So if we follow what it will be doing here, saying there is a reference here, mark it, go there, mark it, and so at the end of the day, the timer holder will be recursively marked as being used. So the garbage collector will see that there is a route down to the timer holder, so he won't be able to let the finalizer be executed.
Okay, so it makes sense. Gotta admit, it makes sense. But then what is the point of the timer holder, and why did it work in your demo?
Because I was cheating. I was cheating just for you. Not for you, just for the audience, okay? Nothing against you, really. So what's the difference between my code and the code that we have in production? It's a tiny detail, but if you take a look at this function, this call to the console, it's a static call. What I mean by the static call, I mean that the compiler will see that we are calling a static function. So it doesn't need to provide this implicit parameter as the hidden first parameter of the function. So there is no such link here. There is no link to the meter metric. So
okay. So this concludes this case. What have we learned here? Sorry, we've learned a few things. The first thing is that you can't trust Christophe to make a repro. The second thing is that in our code, the meter type did not implement iDisposable. Well, that's our mistake. So developer couldn't call dispose on it. And it turns out that because of this reference cycle, the finalizer of the timer cannot kick in, and so our timers are immortal. And so during the lifetime of the application, we keep allocating more timers, and they generate contention whenever they tick. Yeah. And this leads to this progressive increase of contention.
Yeah. And I just sorry to interrupt, but when Kevin was making fun of my ability to reproduce, it's something very important. You know, when you're trying to reproduce the problem, try to be in the real condition. Okay.
Can I finish my sentence?
Sure, go ahead.
Okay. So what was I saying again?
I think you were saying that we've seen some of the way we are.
No, I wasn't done explaining. Please.
Okay.
Thank you. So why did it happen with that version in particular? It's because before then we always used Meter in singleton class, and this was the first version of the application where we used Meter in a transient type, and that's why it revealed the leak, and that's why we couldn't see it just looking at the code changes.
The code changes.
And so the fix has been obviously to implement iDisposable in Meter. And also because it was a lot of work to change all the code that calls Meter, and we wanted a quick mitigation, so we also implemented a finalizer in Meter, which is outside of the reference cycle, and so this finalizer worked properly and mitigating the issue.
Like I explained.
Yeah. And so through this investigation, we've seen this mindset I was talking about. Whenever facing a complex issue that you don't understand, first start by gathering as much data as you can. Make sure this is data that you can trust. Then try to put that data into context, use tools to dig deeper, and try to elaborate a theory about what is going on. And then don't forget to verify what you think, and then try again and again until you manage to solve the problem. So this was a fairly straightforward case. I think many people here knew about this kind of gotcha with timers. So we prepared a second case, which is going to be a tiny bit trickier. Yeah. So Christophe, can you introduce it?
Yes. So in that particular case, we've seen a brutal increase of the number of exceptions that are managed by our application. What I mean by that is if you have a try-catch block and there is an exception that is thrown inside the try block, it's called an exception that you can manage, and it's what we call the third chance exception, and your code catch the exception, usually make a log, and that's it. But this has a true impact on performance. So we are monitoring this number. And here you see that we started from something very low. I can't say it's 0 because it ended up at almost 1 million exceptions per minute.
Yeah, so that's like 20,000 per second, pretty much.
20,000 per second. So I guess that the application would be on its knees. So.
Well, surprisingly, the application was still running fine and answering to requests just as normal. In fact, it took us nearly 24 hours to notice the problem. So
good monitoring. Great monitoring.
Except a slight increase in CPU, there was nothing wrong with the application.
Okay. So what would be the next step? Remember, we are in a real-world application, so we expect to have logs in our application. And as I said at the beginning, when you are doing a try-catch block, in the catch block, it's a good practice to log the exception that your code has seen in the catch block. So I'm expecting that we have killed our logging system, and it's just swamped by all the exceptions.
Yeah, you kind of spoiled the end here. So there was nothing in the logs. So maybe it means that we forgot to log the exception in the catch block. I don't know.
No finger pointing, we said, about developers. No. So when you are in that stage, you are like, okay, we have millions of exceptions, but I don't know which exceptions. So how could you do that? I know a trick, which is using a tool from sysinternals. And this is the tool that we are usually using to take a memory snapshot of an application and get a memory dump file. And this tool is called procdump. But you can also use procdump to list, to view in the console all the exceptions that are thrown in your code and end up into a catch block. And for that, you are using this command line, which is -e for exception, 1 for first chance exception, and the -f is for the filter. And you give nothing for a filter. And if you run this with the process ID of your faulting application, then you will see the name of the type of all the exceptions that are thrown.
So it's very important to mention that in this talk we are describing what we did back then for this investigation and not what you should do. You shouldn't use procdump to trace the exception. Instead, you should use ETW events, which are much less intrusive. But back then, we didn't know that, so we used procdump. And it turns out that procdump was so intrusive that after attaching to the process, we would see 3-4 exceptions, and then it will slow down the process so much that it wouldn't be able to do anything more. But it helped us to see that the exceptions thrown are thread abort exceptions.
Does it mean that we have some code that are calling thread.abort exception?
So I checked the source code, looking specifically for thread.abort call, and this is not a joke. It was really like that. I found a call to thread.abort, but it was removed from the code base 1 week before the release.
Sure.
And so, in fact, it was so crazy that I actually went to a production server and decompiled the assembly there to make sure that the code wasn't there. And indeed, it wasn't there.
Okay, so this is something very important. Remember, when you are gathering information for understanding what's going on, you need to trust what you are looking at. So here we have a kind of coincidence. But going into a server or asking customers to decompile the binary, the assembly, to ensure that the code that is running is really what you think is running, it's really, really important. So don't be scared. There is nothing wrong doing that.
And actually, we were talking with some guys at the diagnostic team at Microsoft, and they were wondering why we would ever use a decompiler since we have the source code of .NET Core and the source code of our application. And the reason is simply that this is the only way to be absolutely certain of that you know what you are executing.
Yep.
Anyway, so nothing is called thread.abort. But to get more information, I attached a remote debugger and tried to see what was going on. And I noticed that from time to time, in between the thread abort exception, we would have a cannot unload app domain exception. And this is very interesting because this application is using ASP.NET. And ASP.NET is known to unload the app domain when you make a change to a configuration file. And whenever you unload an app domain, it aborts all the threads in the domain. So it seems like a good candidate. So it just means that somebody is editing the configuration file on the server.
And saving 20,000 times the configuration file?
Don't you have this habit that you press Ctrl+S every time you type a word?
Not 20. I mean, yes, but not that fast.
Okay, okay.
It must be something different.
Fine. Still looking with the debugger, I noticed something weird. Is that the thread abort exception was always happening with the same core stack.
So if you think about it, it makes kind of sense, because if we have a bug, you can expect that we just have one bug that causes the same effect. So
yeah, well, I disagree on that, because if you are aborting threads, then you have really no reason to have the abort occurring every time at the exact same point in the core stack. And so since I was wondering about that, I checked the thread ID, and the thread abort exception is always happening in the same thread.
Always the same thread?
Always the same thread.
20,000 times?
Yeah,
okay,
but if you check the code, the source code, it makes sense. I mean, it gets pretty obvious when you see it. So this is the core stack where the thread abort exception was happening. And so we have a method. Inside we have an infinite loop.
Okay.
And inside we do some processing. In fact, we are uploading a file to a remote server. And then we sleep for 15 minutes. So why are we not using a timer here? I don't know. Maybe the developer was afraid of leaking timers.
Probably. Probably.
But the important part here is that it's happening in the try-catch block, and it's written purposefully in such a way that if an error happens, we retry immediately. That's because we expect to have some transient network error during the uploading, and we just want to retry. So now imagine this code is running, then there is a change in the configuration file, so ASP.NET aborts the thread, but so it throws an exception, we get into the catch block, but then we exit, and then we keep going on the while loop, so the abdomen tries to abort the thread again, so it throws a new exception, but we are inside the strike block, so we catch it, so we stay in the loop. So the abdomen try to abort the thread, and I think you get the idea. And
yeah,
it happens 20,000 times.
I'm trying to write down your very nice story because I like very nice story. So it could be good, except that we are talking about a thread abort exception, and this is not how a thread abort exception is working.
Yeah.
So if I can just resume what you were saying. So
okay.
We are in an infinite loop. There is a try-catch block, and in the middle there is an exception. Okay, so the exception is caught in the catch block. It's a thread abort exception, so we do whatever we want with the X here, and then we execute whatever we want, we log, we do what we want. But the difference between this kind of exception and the rest of the exception is that after the last execution of your code, the runtime will ensure that the thread abort exception is rethrown and rethrown outside of your try block. So you will just have like an infinite loop that stops at the first iteration.
So you're saying that it is going to be thrown only one time?
Yes.
So this is a very nice story, Christophe. You know, I respect you a lot. You are a very wise man, an expert. You graduated in 1989. Yes. You are a master of abductive thinking. But in this case, just look at the facts.
Okay.
Just the fact. We have 20,000 exceptions per second. They are all happening on the same call stack.
Here?
Yeah, and always with the same thread ID. And so just looking at the fact and quoting somebody more famous than me, he's saying with his word that you are wrong, Christophe.
I like this. I like this. So again, remember, we have the 3 steps. And here we are at the end of the step 2. We mean that we have facts, we have stuff that we can see, and we know how it's supposed to behave. So we have to verify if the facts are wrong or if the guy who say it behaves like this is wrong. So I will double check that. Again, like the finalizer, you remember the finalizer? So if I'm going to, not here, and I think I have something that looks like your nice method. So I have a method with an infinite loop. I have a try-catch block. And in the catch block, I'm just pushing to the console the name of the exception.
So you are logging the exception.
So I'm logging the exception. I was not the, okay, I'm logging the exception. So how can I test that? I'm creating a thread that will be calling my infinite loop method. Then I'm starting the thread, and when I'm pushing the button, I will abort the thread.
Yeah, never do that at home.
Yeah, don't do that, just for the audience, all that stuff. So if I'm running this, I'm expecting to see press enter to terminate the thread working, and I'm pressing just one line with thread abort exceptions.
And I'm telling you that just from the fact, we already know that your console is going to be flooded by thread abort exceptions.
Let's let the audience be the judge here. I'm running the code. I have like press enter to terminate, working, and ta-da!
So it's very important in this job to learn from your mistakes.
Yes.
And remember the mistake I did earlier, it was trusting Christophe to make a repro. And so if we
not
check,
always, okay? Not always my fault.
If we check the project, then we see that it's running in debug mode, and it's very important to do your repro in the release mode because it changes a lot of things, it triggers a lot of optimization, and this can change the behavior of your application.
My mistake. My mistake.
So this time,
okay, I run it, working, and
so another part that is important in this job is not giving up.
Okay.
And once again, Christophe is trying to trick you because he's running the project with any CPU. And if you're running with the default settings, then it will run your program in 32 bits. And on our server, it is running in 64 bits.
You're right.
And
My
a lot
mistake
of lots of things change. Sorry.
Yes.
We are using pointers that have double the size, and so maybe it's overflowing some kind of data structure, and you never know.
Sure. Overflowing of a pointer. Yeah. Yes. So what I'm supposed to? I'm just running.
Pointer size.
Pointer size. No. So it can't be. It can't be the pointer. So here again, we have a conflict between different view of the same reality. So
well, between reality and your view.
Yes. Okay. So my reality is supposed to be like this. When you are calling thread.abort, it's a kind of asynchronous call. What I mean by asynchronous, I mean that the call itself will set a flag on the thread object, and in the flow of execution of this thread, when it reaches what we call safe place by the just-in-time compiler, then it will throw the thread abort exception to be sure that it's in the right thread that the thread abort exception will be thrown. And then this code checks that if you are in a try-catch block, at the end of the catch block, it'll ensure that the exception, so my mistake again, will be rethrown but outside of any try block. So that's my view of the reality.
Who is rethrowing the exception?
The code that is generated by the just-in-time compiler.
Okay, so that's very interesting because another thing that changed when we are running in 64-bit with .NET Framework is that you will be using a ReuJIT, which is the new JIT, well, kind of new. And who say new say bugs. And so maybe we run into a bug in the JIT. And there is one way to find out.
Okay.
Is if you open the application configuration file.
Okay.
And so time for some live coding. If you could add a runtime node.
A runtime node? I'm too old for that. Runtime node. And
here you can add a key which is use legacy JIT.
Use legacy.
You're doing it on purpose. So
no. JIT like this?
No, I see it. So
use
Christophe?
Legacy. What? What did I do? Legacy like JIT like this?
Put it in another node.
What? You want another node? Oh, you mean this?
So
sorry.
Use legacy JIT.
I mean, there is no auto-completion, so I just get lost. Legacy JIT like this or like this?
JIT.
Okay.
So he's doing that because we gave the same talk at .next. No, it was .NET Developer Days, and he did a typo on purpose here, and so it didn't work. And I was on the stage wondering why it wasn't working. So now I'm careful.
Okay. Runtime.
So enabled equals false, please.
With uppercase. Enabled.
Enabled. Oh, come on.
Equal false or true?
Yeah, false.
Sure, because it's use legacy, so I'm expecting true in your demo, no?
Yeah.
Yeah. Don't thank me, okay? It's I'm just saving the demo. So when I'm doing this, I'm telling the runtime that I want to use the old just-in-time compiler when the application will be running. So we will be in release 64-bit with the long pointers.
Yeah. And
with the old just-in-time compiler.
Yeah.
Run it. Working and just one line.
And so indeed, we've confirmed that there is a bug in the JIT. So the first thing we did is reporting it to Microsoft.
Because we are good citizens.
Yeah. So they told us that they would not fix it. But they have good reasons. It's just that apparently it's a very complex fix. Yeah. The bug happened only on very specific code. And it's only on .NET Framework because you don't have thread abort on .NET Core. And no abort, no problem. So to fix it in our code base, what we did is adding another catch block where we specifically catch the thread abort exception. and then we rethrow it ourselves.
Yeah.
So that's some code that I never imagined I would be writing.
Okay.
And so through this case, we illustrated the importance of verifying your assumption, which may be incorrect. And in fact, remember how nothing was logged? It was especially hard to find the cause of the problem because we didn't show it, but in this code, there is actually some logging going on in the catch block. But it turns out that whenever you unload the abdomen, you abort the thread. And so the thread of the asynchronous logger was being aborted. And that's why we didn't get any log.
Yeah.
But if you go with the right mindset and methodically confirm each of your assumptions, sooner or later, you will get to the root of the problem.
Often later, okay. Okay, so we also wanted to show you that sometimes you need to have your own tool, like what I've did with the usage of CLRMD. Sometimes you need to extend the tool that you are using, like what Kevin did with WinDBG, because it just helps you to scale in your investigation. So don't be scared. Don't be scared. You can do it, and it will save you a lot of time. I think the most important part, as you've seen, is like you never, ever assume that you know what's going on. Because if what you see is not like what the model that you have in mind, you need to verify, always. And more often than not, you will see that even with a wise and a long career, you might be wrong. Okay? So we are also, we have written some blog posts. So if you want to dig a little bit further inside the tooling, inside the kind of investigation, you just look for the Criteo Labs blog series. And you can touch us on Twitter if you have any question. And I would like to thank you for your patience. So I know this is the last session of the day before the craziness will start. So we have 3 minutes, but since it's the last session, if you want to ask more questions, we are free to answer. No question. One question. Yeah, sorry.
What's your favorite decompiler?
What's my favorite decompiler? Yeah. I'm old enough to remember the reflector time. So I used to use reflector before it was no more reflector. But I'm using ILSpy. You can use, what is your?
So personally, there is .pic from JetBrains that I like a lot to navigate the code, but it's painfully slow to open. So if there are JetBrains guy in the room, please optimize that thing. And also there is dnspy, which is, not as practical than .pic, but it allows us to live debug a process, which is incredible.
Yes, you can set breakpoints and everything. You don't need to have the source code. It's much more than just a decompiler.
Which one was that?
dnspy.
dnspy. DN, sorry for the French accents, dnspy. Sorry, just below the light.
What drives your decision to use complex debugging stuffs, like attaching a remote debugger using without DBG, compared to instrumenting the code and make a deployment, a new deployment that gives more logs or things like that?
Okay, so the question was why did you decide to use like a remote debugger instead of having a custom build with more instrumentation inside? I think you can answer this one.
Well, I can give a few answers. The first one is time. This is a small leak, or for the thread abortics. Well, we have 2 cases here. We presented 2. For the leak, it's small enough that you wouldn't see it on a dev computer, so it's really hard to instrument, and you don't even know where to instrument, actually.
Yes.
And for the thread abort exception, it's even worse, since we didn't even know what triggers it. Yeah. In fact, so I mentioned that the abdomen is unloaded when you change the configuration file, and the configuration file was changed by the deployer, the application that deploys the files in production. And so that's something that is very hard to reproduce.
Yeah.
And that's why, as much as possible, we prefer to get the information directly from the memory dump, because you know that the issue is there. And if we cannot figure it out, then we add more traces to the code. And
yes, and another reason is also that sometimes you can't reproduce the problem. We are talking about thousands of servers, okay, in 6 data centers, something like this. So when we have one that is misbehaving, and we try to keep it for a short period of time, but because we have the repro over there. And if we change a little bit the code, add some logs, add some stuff, you might change the way the threads are behaving. So maybe it will work. That's another reason.
You
Yes.
solve the problem by changing
Yeah.
the code.
Yeah.
And you keep the trace because it solves the issue.
Exactly. Yeah. Any other question? Yes?
How do you test your code before putting it into production server?
How do we test the code before putting it on production server? We test a lot. We test a lot. So we have a lot of unit tests in the code. So it's even...
I ask about this complex problem like you described us.
So we have the unit test, we have the test that run at the build, then we have some dedicated server on which we test several applications because we have like microservices communicating to each other. So we have this first, the last step before going to production. We have pre-prod servers, and if you just miss the case where the installer application changed the configuration file, then you just don't miss it. Because we are doing the test in a question of hours, not in a question of days. And maybe in this environment, we don't deploy until the end of the test. So,
but for those specific issues, we don't test it.
Yeah.
I mean, I don't know how to test that.
no, I don't know.
How much time did originally take to figure out these both issues?
So how much time did it take?
Days, yeah.
Days, yes.
2 to 3 days, yeah. For those investigations.
The first one and the second one?
Yeah.
Yeah.
They took about the same time, I think.
Yeah.
But then we have an investigation that took weeks.
Yes, we have longer investigation because here it's like kind of simple because we showed you the metric that was interesting and then the part of the code and then because with large memory dump also it takes a lot of time. That's why we try to automate. If you look for the blog and on my name also on GitHub and Kevin's name, you will find all the source code of the extension. You will also find the source code of applications that are using CLRMD that you could use to make your own tool to automate all the process. It's really, really simple. Believe me, it's really, really simple. So try to automate your own investigation. It will save you a lot of time. So for example, for the timer, we were doing a lot of stuff like manually. And then we wrote our own WinDBG extension, and we just added a new command called timer information. And so now we just bang TI, and we get the list of all the timers with all the callbacks. So we learn from what we are experiencing, and we are trying to minimize the number of time that we are spending on a manual process.